So this is a brand new. Normally, Noah, I would get to this unit at the end of Physics 11. I would do, similar to forces, a one-dimensional version, but you would see all the concepts. And then in Phys 12, I would add some two-dimensional stuff. Here, because it's brand new, I've kind of tweaked my lessons, and I'm going to introduce the concepts. We're going to focus in terms of homework and tests and quizzes on the one-dimensional stuff. I'll mention the two-dimensional every once in a while. I'll say, hey, here's how we could throw a vector in. But then I'll say to you, now that I've shown you how we could do it, I'm not going to assess you on that. I'm not going to test you on that. Is that okay? So the unit is called work and energy and power. Part of the challenge is all three of those words have English meanings that are very different from their physics meanings. If you say, I'm doing work, what you probably mean is, I'm getting tired. That's not what work means in physics. When you say you have energy, you probably are saying, I'm the opposite of being tired. It's not what it means in physics. So we're going to have to go very meticulously. We're going to start out with something called the work-energy theorem. This is going to define what work is in physics and how it relates to energy. So work is a scalar. Do me a favor, underline that. That's going to be hugely useful and important. Because it's a scalar, hey, we can just add or subtract stuff without doing tip to tail. It's defined as the product. When I say product, what mathematical operation is that? So where it says W equals, put a little times sign there. Of the force component in the direction of motion and the distance moved. Say what? Work is force times distance. Except the force and the distance have to be in the same direction. If you're pushing up and moving sideways, no work. Okay? If the force is up and you're moving something sideways, no work. Okay. Units. Well, what do I measure force in? Newtons. What do I measure distance in? So technically, the units for work is a Newton meter, but we've given that a name. We call that a joule, symbol capital J, named after a scientist whose last name was Joule. But it's technically a Newton meter. The same way a Newton is technically a kilogram meter per second squared, because it's mass times acceleration. How much work does Connor do when lifting? Underline the word lifting. A 50 kilogram mass up to a height of 5 meters. What's this question asking me to find? How much what? Work. Work is force times distance. Let's write that down. Don't write this. You can if you want. Visualize the free body diagram. Let's assume Connor is doing minimum work. He's lifting it at a constant speed. Okay? He is applying a force up. That's his lifting force. I don't know his lifting force. Get the obvious one. If Connor is lifting it up at a constant speed, can we agree that the lifting force is the same size as gravity? Okay. So I'm going to say it's, for the F, I'm going to replace the F with mg. And since it's a vertical distance, we often use a lowercase h for height. That there, mgh, is the equation for how much work you do lifting something. It's the special case of force times distance for lifting something. It's mgh. Okay? See how we kind of derived it? It's sort of on your formula sheet in a disguised manner, so don't freak out. You don't need to memorize it. Anyways, what was the mass? 50. G, 9.8. 5 meters. How much work? I can do that in my head. going to be 490 times 5. 500 times 5 will be 2,500. So it's 2450? Double check me. 2450? Okay. Units, it's work. What are the units for work? Joules, and it's time again to start memorizing some new units because we haven't done any new units yet this year. Okay. Is that a lot? 50 kilograms, about 120 pounds. You know what? That'd be like piggybacking someone. 5 meters. It's about a flight of stairs and a half. That's how much work, how much energy you would burn up giving somebody a piggyback up a flight and a half of stairs. Okay. Doesn't matter whether the stairs are shallow or steep because we're just talking about the height. If it was shallow stairs, it would take you longer to do the piggyback. If it was steeper stairs, you would get there quicker, but you're still doing the same amount of work. Force times distance. Suppose Connor is unable to lift the mass straight up. Instead, he decides to push the mass up a ramp at an angle of 30 degrees. If he ends up at the same height, how much work will he do? Let's assume we're going to ignore friction. We're going to dolp. So here's our ramp. There's the mass. .30 degrees. And the height here is apparently 5 meters. Okay. Now, instead of, don't write this down, instead of lifting straight up, Connor is going to be pushing up the ramp. Okay? So what we want to figure out is Connor's applied force, how hard he's pushing. This is a job for a... Yeah, it's also a nice review of forces, Aiden, which is the other reason I always do this unit right after forces. Is the first couple lessons, we're rejogging our memory. What are the forces acting on this block, Aiden? Get the obvious one. Okay. And we always pause with the ramp. We say break it up into mg perpendicular, mg parallel, and then there's a normal force. Again, let's assume that Connor is doing the minimum amount of work. So we're going to say A is 0. You're just keeping it going at a constant speed. Okay? Now, what work is force times distance? Which force? In this case, it's the applied force. But the force and the distance have to be in the same direction. So the distance that we want is that. Not a force, it's a distance. So, got that triangle? Over here, a little smaller, redraw the same triangle, but this time we're going to put the 5 meters and the D there. And the 30. We're not going to use forces. We're going to use actually just good old trig. That D, opposite, adjacent, or hypotenuse. That 5. Oh, sorry. Color. That 5. Which trig function? O and H. Sine. Okay, so I'm going to make a little note here. It turns out sine 30 equals 5 over D. How would I get the D by itself? Well, dividing by D on the right on the bottom. Ugh. Oh, that's the same as timesing by D there, yes? Remember all these little tricks of the trade we picked up, Noah? And then how would I get the sine 30 over? How to move the sine 30 over to get the d by itself? Which one of those is correct? You said multiply, you said divide. The good news, one of those is right. What's the sine 30? Noah, look up. What's the sine 30 doing to the d? So, yes. So here's what I'm arguing. D is 5 divided by sine 30. What's d the same as? 5 divided by sine 30. I'm not going to evaluate it. I'm just going to leave it like that. Okay. Let's go back to this equation right here. I don't know F applied. But wait a minute. Connor, if you're pushing at a constant speed, if A is 0, what must F applied be exactly the same size as? Parallel, right? That's the tug of war on the ramp. With me? So I'm going to argue that I can replace F applied with mg parallel. They're the same size. Okay, so let's write down W equals mg parallel times d. mg parallel, 2 lines. So here's what I get. W equals mg times sine 30. And then what did we say d was equal to? 5 divided by sine 30. What happens to the sine 30s? In fact, you know what? We get mgh again, don't we? The same equation up here. Isn't it going to be 50 times 9.8 times 5, even though there's a ramp? What I've just done, Noah, I've proved to you, work is a scalar. It doesn't care about directions at all. If you want to go up a ramp, you can go ahead and work it out that way if you want to, but all your trig stuff is going to cancel, and it's going to be mathematically just the same as if you lifted it straight up, baby. What a ramp is, it's an example of a simple machine. The work is going to be the same. I forgot to put an answer. It's going to be 2450 joules. But if you actually calculate how hard Connor had to push, can you actually type in mass m5 times 9.8 times sine 30? Could you do that, please? On your calculator, could you go 5 times 9.8? Yeah, Josh, you too, times sine 30. We're going. What do you get? 5 times 9.8 times sine 30. Aiden, what do you get? 24.5? Is that right? Now compare that with lifting straight up. Can you go 50 times 9.8? 49? Yes? 50, sorry, 490, yes? Yeah. And sorry, this should have been not 200, should have been 245, right? 50 times 9.8, did I say 5? 50 times 9.8 times sine 30 on your calculator? Yes? Okay. So how big is mg parallel? 245. How big is lifting straight up? 490. What a ramp does, it doesn't change how much work you have to do. It drops the force in half, but it doubles the distance. If you go 5 divided by sine 30, you'll find that's 10. Double the distance, but you can cut the force in half. We're not going to look at this subgroup of physics, but these are called simple machines. A machine in physics is something that reduces the amount of force required by increasing the distance. The amount of work remains the same, But simple machines are the greatest inventions in human history. They allowed us to build the pyramids. They allow us to do everything. Anything in engineering that moves something almost always is a series of simple machines. There are, I'm blanking because I'm tired, I forget. I think there's 5 simple machines. There's the lever, the wedge, the ramp, the screw, the wheel? Can't remember. That's an aside. What that example was to prove to you, Mark, that work is a scalar. So who cares about ramps? And work is what times what? Force times distance. Lifting work is mgh. Okay? So if there's friction on the ramp, because in real life there will be some friction, you'll end up doing slightly more work, but the force required will still be way smaller than lifting it up. So it's a force multiplier. A simple machine like a ramp allows a single person to raise a much bigger object than they could if they just tried to lift it up. Okay. Example 3. A ball on the end of a rope is following a circular path because of a constant force exerted on the ball by the rope in the direction toward the center of the circle. Look up, like this. So those of you at home can't see what I'm doing. I have a ball on the end of a string and I'm spinning it around my head, holding on to the string. Okay? How much work is being done on the ball by this force? Well, how do we calculate work? What's our new equation? So let's write that down. Mr. Duke, they didn't give me a force. They didn't give me a distance. No, they didn't. Here's why. Look up. The answer is 0. What was on the first page, in the first paragraph, what was the condition that I gave you about the force and the distance? I said the force and the distance had to be in the same what? Same direction. Here, the force is inwards, but the distance is sideways, no work. Okay? No work. Let me give you another example. Pause the video for a second. You can have negative work if the work and the force are in the same direction. That's positive work. If the work and the force are in the opposite direction, that's negative work. You with me, Josh, or is there somebody at the door window? Okay? You with me? Because you're zoning out a few times. I need you here. This is the new stuff. So, in general, a force in the same direction as motion, like F1 below, does positive work. A force in the opposite direction does negative work. What does negative work mean? It means you're losing energy, not gaining energy. So it's not a direction, it's a magnitude. The magnitude's getting smaller. So, although work can be positive or negative, it's not a vector, it has no direction. What if the force is at an angle? Did I say angle? Okay. We would go like this. There's the force. Hey, this looks like a lawnmower question. We would break it up into Fx and Fy, and there's theta. Look at the little picture, look at the direction of the distance. Which of these 3 forces, F, Fy, or Fx, is in the same direction as the distance? Don't overcomplicate it. So here we would say work equals Fx times distance. Fx, which trig function? Well, which trig function was Fy? So can you tell me which trig function Fx would be? Of course you can. In fact, if you want the generic formula for work, the actual formula for work, it's this. Work equals force times distance cosine theta. I didn't put this on your formula sheet because I'm not going to ask you it. I'm showing this to you because I'm a nerd and I do like to show you that this still works if there is an angle. But for the rest of the unit, I'm going to keep everything in a nice straight line. But just for giggles, get your calculator out. What if theta is 0 degrees? What's the cosine of 0? What? And then you get the equation that I led off with, force times distance times 1. Okay? Oh, what if theta is 90 degrees, like Wes piggybacking Sean? What's the cosine of 90? That's why under that, no work. So it works. What if we're pulling this way? Sorry, we're moving this way, but the force is that way. How big an angle is that right there? What's the cosine of 180 degrees? It'd be really cool if that was -1, and if that explained why it's is it? Oh, bonus. That's why that's negative work. Okay. So this is the actual general equation for work. Didn't put it on your formula sheet. I always show it to the kids, but from now on, the most you'll have to deal with is, opposite direction, make the work negative, not positive. Okay? Okay. There's a second condition. So if you look way back here, you can turn the page, but I said the work done by a constant, an unchanging force. Yep.
We have a class camp,
Yep.
right? So I'll do your room next after Dennis.
No problem.
Thank you.
Work done by a constant, unchanging force is force times distance. What if we have a changing force? What if we're increasing how hard we pull or push? Second definition of work, it's the area underneath a force versus distance graph. Val turned the page after I said to turn the page. Good. Okay. So here is a force versus distance graph. And the question asks, how much work is done moving this object from 2 meters to 6 meters? Well, let's all draw a little line going down at 2 meters, a little line going down at 6 meters. First of all, do you notice, Marcus, the force is changing. It starts out how big? And it finishes up how big? So I can't go force times distance. It's a changing force. What is the amount of work is that area. Don't color that in just yet. What shape is that? What do you call 2 parallel sides and 2 non-parallel sides? It starts with a T. TR. Not a triangle. TRA. TRAP. It's a trapezoid. Trapezoid, 2 parallel sides, 2 non-parallel sides. And I always ask, because there is one out there, anybody know the area, the formula for the area of a trapezoid? There is a formula. Sometimes, occasionally I'll have an ESL student from whatever country who knows it. We don't teach it because it's redundant. There is a lovely equation for the area of a trapezoid, but any trapezoid is always a triangle and a rectangle. And those we do have area equations for. So do me a favor, draw that little line in like that. You'll always be able to break a trapezoid up into a triangle and a rectangle. Let's put a big number 1 and circle it in the rectangle. That'll be area 1. Let's put a big 2 right there. So area 1, I'll use an A and a subscripted 1. How do you find the area of a rectangle? Loud and proud. It's going to be length times width. What's the length of that rectangle? Read it from the graph, please. Don't say 6. Yeah? Did you not? Oh. I thought I didn't hear the knock. We'll pause for a second. Area of let's review, because we had a little break there as we went out for the room cleaning. Work is also the area underneath a force versus distance graph. And you'll know, Noah, because Oh, they gave me a graph, and on the y-axis is force, on the x-axis is distance, and work is what times what? Force times distance. So it's kind of obvious that way. It's an integral if you're really being fussy, yes. If it's it'll either be a triangle or a rectangle or a trapezoid. If it's a trapezoid, well, it's a rectangle and a triangle. You can break up any trapezoid into that. So area of a rectangle is length times width. What's the length of this rectangle here? Don't say 6. From 2 to 6 would be? Okay. What's the height of this rectangle? I think that's supposed to be 2 in my sketch. In your head? That's the area of the rectangle. Then the second area is a triangle. What's the area of a triangle? What formula is that? Aiden, I notice you have your formula sheet on the back page there. Did I give you the area of a triangle? Somewhere where there's a picture of a triangle? What is the formula for the area of a triangle? I usually just write it as base times height over 2. It's half the base times the height. Okay. That's maybe worth memorizing just as a mathematical fact, but it's on your formula sheet. I don't think I gave you length times width on your formula sheet. I figured it was fair game for me to assume you know how to find the area of a rectangle. What's the base of this triangle? How long? People, how long? 4. What's the height of that rectangle? I think the height is this right here, is it not? What's the height of that rectangle? Did you say 1? Oh, I thought I heard 4. Sorry. And then divided by 2. Mark it in your head. 4 times 1 divided by 2. Thank you. So, what's the total area underneath this force versus distance graph between 2 and 6? We're finding that area. What is the total area? What? Say it again. 10 what? Joules, and that's how much work was done moving this object from 2 meters to 6 meters. I want you to think about how powerful this was. Normally, work is force times distance, and F equals what, ma? We don't know the mass. We don't know the acceleration. We know nothing here in this question except, the distance that we moved it and the 2 forces, the force, the area. So they don't even need to give me the mass. Okay? So work equals 10 joules. I'll put a period after the 0 to go to 2 sig figs just because I'm a nerd that way. Work is what times what? Force times distance. Energy is the ability to do work. It's the ability to apply a force over a distance. If an object has energy, it can apply a force over a distance. And there are many, 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 many forms of energy. There's the energy of motion. This is called kinetic energy. Any moving object has kinetic energy, because if it hits something, it can apply a force over a distance. Heat is a form of energy. Heat is usually created by friction. You may notice if you rub your hands together, you can feel the heat generated from friction. Okay? And by the way, really what that is, that's the force of friction times the distance that if you add up all the small distances when you're rubbing your hands together, you could actually calculate how much heat you were generating. It's gravitational potential energy. This is energy that you store when you lift an object. Stored, that's what potential means. Stored energy in a lifted object. Oop. It's energy that an object has due to its position. Any type of stored energy is called potential energy. So for example, a battery has electric potential energy, potential stored, electric because I can convert this into electricity. And once I run it into some kind of a device that can apply a force over a distance. By the way, it's applying a force over a distance on electrons, but it's still doing work. Chemical potential energy, gunpowder, or the food that you eat. What does potential mean? Stored. And in this case, it comes from chemicals. Other forms, sound is a type of energy. Elastic energy, when you stretch a rubber band, you've done a force times distance. You've stored energy in that rubber band, and when you let it go, it can apply a force over a distance. Nuclear energy, that's the energy stored within the nucleus of an atom. There are many, many, many different types of energies. We're going to look at two main types, kinetic and potential. Example 5. Sometimes when we do work, we make things move. Sometimes when you apply a force over a distance on an object, it starts to move. We're going to fill in a proof to find an expression for motion energy, kinetic energy. And my brief for kinetic energy is capital K, capital E. Okay. Well, work equals what times what? What's our definition of work? Good. We're going to start there. And then we're going to say, Karn, F equals what? So I can write this as MAD. And then I'm going to do something just a little bit weird. I'm going to multiply by 2 and multiply by a half. And the reason is 2 times a half is 1, so I'm not changing anything. But I'm going to say, I'm going to put a 2 in front of the, I'm going to put a 1/2 in front of the M and a 2 in front of the AD. That's the same equation as MAD. It'll give you the same answer because timesing by 2 and then timesing by half, they just cancel each other out. But then I'm going to go like this, D. Put a little dotted line around the 2AD. Because VF squared equals VI squared plus what? Oh, and if I start at rest, VI squared is 0. What can I replace 2AD with? Okay. Well, you know what? I can replace the 2AD with that if VI squared is not 0. So in the next line, I replace the 2AD with VF squared minus VI squared. And if VI equals 0, we get this, a half MV final squared. This is the amount of energy, this is the amount of work done to get an object moving. It's equal to a half MV squared. I want you to notice, Wes, I didn't put a little vector symbol on the V. It's the speed, not the velocity. So there's an angle. You can use the speed that's at an angle. Remember in the first unit on projectiles, I said, yeah, we're never going to use the slanty one. Here we can, because it's a scalar. Don't need to go components. Here, did I say angle? Who cares? In work and energy. Just to give you an idea of what joules are, in a typical jelly donut, there's about 1 million joules of energy, if you break that down into your food. So a joule is not very big. There's a smaller measure of energy called an erg, and that's about the equivalent of a mosquito push-up, which is a force times the distance. I ran the numbers. It's about 10 to the negative 13 jelly donut. It's about 10 to the negative 7 joules. So an erg is about 0.000000 1 joules. You don't need to know what an erg is, but it's a word that I've seen that has popped up once in a while, so I threw it at you. I'm not going to test you on it. But one of the main applications of work and energy is in sports science. In almost any sport where you swing an object to hit another object. Hockey, hockey puck, hockey stick. Golf, golf club, golf ball. Baseball, baseball bat, baseball. Tennis, tennis racket, tennis ball. Golfer. Anybody here on the golf team? You go, okay. Suppose you want to improve your driving distance. What would have more effect? Doubling the mass of your golf club, making a bigger driver, or doubling the speed at which the club head strikes the ball? That's a good question. Well, kinetic energy, which is what we're talking about here, is equal to a half mv squared. A half mv what? A half mv what? Okay. If I double the mass, this, I have trouble doing it. As a lefty, I have a really hard time doing a good capital E. Sorry, it's messy. If I double the mass, this gets twice as big. But, don't write this down. If I double the V, how much bigger is it? Because of that squared. No, not double. What's 2 squared? 4 times as big. If I double the speed, I'll get 4 times the distance. If I double the mass, I'll get twice the distance. Okay? So, you can write down K equals a half mv squared, since v squared, 2v squared means 4 times distance. And this is why, Noah, the trend over the last 15 years in most sports equipment, the equipment's been getting lighter, which makes the M smaller, but it's so you can swing it faster, because the trade-off, you get way more back in the trade-off because there's a squared on the V. Even if the M gets a bit smaller, if you can increase that V, because that then is squared, you get way more bang for your buck. Way more bang for your buck. Okay? So definitely doubling the speed, 4 times the distance. Doubling the mass, only twice the distance. Is that all right? Yeah. Let's see how much further I'm going to get. Okay. So, what's the energy equation for motion energy, for kinetic energy? A half mv squared. That one is on your formula sheet. Make sure you notice where it is. Ke equals a half mv squared. Sometimes when we do work, we lift an object and give it height energy. This is the example we did with Connor at the beginning of this lesson, and I'm just going to go straight to the punchline. Well, since work equals force times distance, if Connor's lifting it at a constant speed, the force that he's outputting is the same size as mg, and we'll call that distance h. Potential energy, gravitational potential energy, is mgh. The higher I lift something, the more energy I've stored in it. What that really means is if I let it go, when it hits the ground, it'll apply a bigger force times distance. It'll do more work. The heavier the object that I lift is, the more work it will do. Any squareds in this equation? No. So here, unlike the kinetic energy, doubling the mass doubles the energy, doubling the height doubles the energy, as opposed to here, doubling the mass doubles the energy, doubling the speed quadruples the energy. What if you triple the speed? How much further will the golf ball go? 9. Yeah. What if you quadruple the speed? And now you're starting to see that's why we're willing to trade off some mass to increase your club head speed, because you can swing a lighter club far faster than you can swing a heavier club. Okay? There's limits. I mean, I'm not going to make the club so ridiculously light that it has almost no mass, but certainly clubs have become lighter. So we're going to be focusing on, height. H is the height above the reference. It's a scalar. If you're underneath the ground, you would just make the height negative. Okay? Usually we focus on mechanical energy, which has two main types: kinetic, half mv squared, and potential, which is usually going to be mgh. We're going to pause here. We'll pick up with this on Thursday. Thursday, you want to show up with that quiz done, please. Okay? I will be on Teams tomorrow afternoon if you have any questions. Are you all able to access Teams? I've been sending out a Zoom link, but if I just have my Teams app open, are you able to then get my attention and I can then email you a Zoom link if you want to do a shared screen or something like that? Does that work? Okay. So what I'll do is I'll just have my Teams app open on my phone right next to me, and I'll have it so that if you ping me, I'll get your attention. You get my attention right away. Okay. Thursday, well, right now, what would you prefer? Would you prefer your test Friday or would you prefer your test Monday? Okay. So Thursday will mark the take-home quiz. Friday I'll finish off this lesson Thursday probably. Friday, since I see I'll be doing another lesson, but that'll also be a bunch of Q&A about forces, and I'll email out a forces tutorial that I've done on YouTube today or tomorrow as well, and that way you got something you can watch over the weekend. Okay? Also, can you then remind me on Friday or Thursday, I'll give you some hints. I'll go through your ultimate review and tell you which questions I like, and I'll give you some fairly blatant hints about what you're going to see on your test. Okay? There's about 20 minutes left. You can work on the take-home quiz, work on your other homework.